Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter, we're going to be looking at exploratory data analysis. What we're going to be looking at in exploratory data analysis usually begins with descriptive statistics, just looking at the univariate statistics data of each of the individual variables. And then we'll be looking at the distribution of those variables. And then we'll look at the calculation of coefficients to look for relationships that might exist between them. And then we'll talk about outliers and how to deal with them, and exploring nonlinear relationships, testing the assumption that the different samples were made from the same population, extracting and examining crosstab frequencies of the data, looking at different statistics in cross-tabulation forms, and using multivariate methods like factor analysis and principal component analysis to detect linear relationships within the data. These are all going to be the processes that are going to be part of the exploratory data analysis, all of which begins before we even begin to start to create our applied predictive models. So as I mentioned, this process begins with univariate analysis, and that's the simplest form of statistical analysis. It's really just looking at the individual fields, columns, one at a time, and looking at their key descriptive statistics. And for KNIME, we're going to use the statistics node to do that. What I'm going to do here is I've got a CSV reader, and I've read some sample data. You can see I've got about 50,000 rows, and it's fictitious donation data for a charity. And what I want to do is I've read this data in with the CSV, and if I right click and look at the actual table that's generated from it, I can see all the individual values for each individual row. And in the column specifications tab, I can also see, we've looked at this before, this is some of the univariate statistics. Like for the string columns like marital status and gender, I can see that gender is male, female, and unknown. And race is unknown, Caucasian, others. I can see the different values in here, and even some upper and lower bounds. But what I'm also going to do now is using the statistics node, and I'm going to run statistics against all the columns of the table. So I'm going to execute this and open the views. Now this is an annoying part of how this one actually works, and it seems to be a glitch in KNIME, but the window is filling beyond the screen, so I'm just going to use a Windows technique where I can right click over this and tell it to maximize it. So I can now get to the buttons and the scroll bars. So I can see here now for each of the columns the minimum, the maximum, mean, standard deviation, and also a little histogram table for the number of occurrences. So like when I look at age, and that's not unexpected, that's a decent histogram. But you can also begin to spot problems that you might notice in ranges, and you know, the total amount given, the average age of my gifter. Is it really likely that I've got somebody who's got a maximum age of 129? There may be some outliers here. But this allows me to at least start by looking at my statistics and saying, do these things make sense to me? Especially when I start to also look at minimum values, maximum values. I can look for negative numbers, for example, in places where that wouldn't make any sense. So that's just simply using the statistics node to do some initial inquiries into what the data looks like. In addition to simply understanding the univariate statistics, we also like to look at each variable and understand any interesting characteristics and problems associated with it by looking at the distribution. Now, continuous variables are usually represented by histograms, and nominal and ordinal variables are usually represented by pie charts or bar charts that sum up their values. Now, plotting histograms is often done by taking the data and using what we call bins. It's a binning process. and it's something we're going to explain in an upcoming chapter in great detail. So for now, just go with me with a simple example that I'm going to present, and we'll talk a lot more about it in an entire chapter. But looking at the values in a histogram form will allow you to see if it's skewed in one way or another. And in that kind of case, we can use the techniques described in the transformation section to change the shape of the variable distribution. So let's look at the distribution and how we're going to do this with KNIME. As I look at the statistics module that we just demonstrated a few slides earlier, and I look at the actual outcome, the statistics table, it actually does provide for me, I make this just a little wider, I get a histogram table, so I can see and I can start to look for things. So right off the bat, for example, I look at total amount given and say I have a very serious, I mean, in terms of gap here, between the 63,000 range, this is heavily skewed to one side. Total is the column that I look at the total number of gifts. And these are not necessarily surprises that more people don't give $63,000 to an organization instead of somewhere between 0 and 100. But it's something I might want to investigate further and actually look a little deeper into some of this data. So in fact, I'm going to come in the node repository here now, and I'm going to grab, now there's a number of histogram charts. This is the current one. The JavaScript are always the ones that are most current and interactive. But I like this local one because it just does a simple binning for me automatically. And until we talk in more detail about binning, this is easier for me to show you. So I'm going to take this histogram and I'm going to tell it I want to create a histogram on the total amount given. Okay, and I don't want anything other than that. I'm not going to total it. And I'm going to create 10 bins. So it's going to break up the amounts into a group of 10 automatically for me. So when I execute this and open the view, okay, I can look at this here and I can say that overwhelmingly the number between 0 and 6,400 is actually way up here. Then it almost all falls off, and I do have a block of missing values. But I have a big chunk of them that are all falling into this category. In fact, over 42,000 of them are falling into that category. So this may be something, again, I can turn around and look at, and I might look at the actual file table, and I'm going to sort this in ascending sequence of total amount given. And as you saw, where there was about 6,200 where it was null values. I literally don't even have a value. And then when I scroll down, okay, I start to see why there's so many. Okay, it starts in 3s and 4s and people just giving a few dollars to my charity, which is 5, 10s. And I'm almost halfway through my file of 46,000 rows, and I'm still only up to $32 a gift. So you can see I look at this and I understand what most people give. And then look at these major people at the very end. In fact, this is so heavily skewed that the last few thousand records of my 50,000 record file are skewing the data heavily. So I may want to look at maybe I want to look at this view and create typical donors and major donors, for example, and break out the data that way. So this is things that I've learned basically by going through and looking at this in the form of either a histogram or by binning nominal data together. Now the last thing I'm going to want to do is I'm going to want to look at the coefficients of correlation. Hopefully you remember that from that portion of the class where we talked about correlation. It measures the strength of the relationship. As one variable goes up, does it have a proportional effect on another variable? It's called the Pearson product movement correlation coefficient, and it's going to measure the strength of the association of those variables. KNIME provides a heavily automated way for us to look at this, and so we can judge the relationship And it's sometimes very useful when we're trying to decide if one field is nothing more than a synonym for another field because they move so perfectly together, and I might choose to do my analysis only on one of them. That's just an example of why I want to know this information before I start my analysis. So let's take a look at how KNIME does this. All right, I'm going to go into the node repository and I'm going to search for correlation. And that's enough, that's what I've got. I'm looking for linear correlation. And I'm going to take this module and connect it up into my data. And I'm going to correlate every column against every other column. And I'm going to do a two-sided instead of a one-sided to the left or right. If you're not familiar with that, boy, you got to send you back to the beginning of the statistics class again. But I'm going to do a two-sided test on all of these and look for correlation. So I'm going to execute and open my view, and notice what it gives me is for every column, basically it compares it against every other column, and the color of the correlation measures the strength of the correlation. So a -1 would be a perfect negative correlation, a +1 would be a perfect 1 correlation would be blue, -1 would be red, and then the shades of you see in between. Well, there's always going to be a diagonal line, because when you compare first name against first name, there's always 100% the correlation is perfect. Last name against last name, so that will always be the case. But I can begin to spot things and say the current year number of gifts definitely has a negative correlation to their age. So it's -0.22. Not a strong correlation, but it is a correlation nonetheless. When I look at this total given and compare that up against the current year total given, the strength of that relationship, again, if I hover, is 0.375. How about comparing total given to the total given from the last 4 years? And I can see that the total strength of this relationship is 0.77. So there is a strong relationship between some of these fields. But depending on the sample of your data, you'll get obviously very different results. But this starts to identify what I would call synonyms, where things are moving together, and you need to understand those relationships when you're doing data science. Now, the detection of outliers is probably going to be one of the most difficult topics for you to put your hands around, because there isn't a clear and standard solution that everybody follows. The basic assumption is that when data does not follow a pattern that it should, it's generally considered and called an outlier. It could result from maybe you've done data entry error, maybe there was an error in the observation that was first recorded, maybe there was a known mechanism that caused a problem. The definition of outliers is therefore subjective, and it's speculative at best. So the decision, however, to exclude an outlier from your study, from your data mining, scoring, etc., you need to be very careful, because it can have a dramatic impact on your solution. So you need to decide, is this truly, for example, in the data set we've been looking at, is it really likely that I've had a person who's 129 years old making donations, or did we just not record their death? These are decisions you have to make before you decide to leave outlier data in or take it out of your model. So the first way we can go about outlier detection, and it's incredibly easy to do in KNIME, is to just set an acceptable range for each variable. And the upper or lower limits of that range will determine anything beyond that range will be rejected. Typically, for example, for continuous variables, we're going to use 3 standard deviations from the mean. Say anything more than 3 standard deviations from the mean is likely a data problem and will be ignored. In the case of ordinal variables, we'd have to say a typical rule might be that the frequency count has to be at least 1% of the available values. So meaning if at least 1% of the population doesn't have this value, it's probably not a good value. the pros here, very easy to implement. The problem is it doesn't take into account the interaction between variables. That's ignored. So you might look at a variable and say that an employee's salary or the age is I don't want anybody more than 3 standard deviations from the mean age. But you might look and say age might have a tremendous impact on gifting, for example, that we've been working on. Meaning a lot of people who get very old have a lot of money to give away at the end of their life. And by ignoring potential older people out of your model, you could be significantly altering the model. So really, you should really only use this technique after you've attempted to reshape the variable distribution using some form of transformation. If you're unable to do it, then you can go ahead with this method. Now, a second method would be one where we would use a model that we've actually created on a dependent variable with a set of independent variables that fit that candidate model. For example, like least squares or a regression model. And then observations that show a large deviation from that model are deemed outliers. Let me give you an example. Remember when we looked at our regression model and we showed how one stray outlier point significantly changed the slope of the regression line. And if we did some research into that data point and decided that data point was invalid because it didn't fit well into the rest of the model. The problem is with this form, I don't always use one method. In fact, you're going to discover right away, I'm going to create a decision tree. I'm going to use a linear regression model. I'm going to create a support vector machine. And all of these different models, and I'm going to find the one that creates the best measurable result for me. So the problem is if you're removing outliers based on the model that you've chosen, that model may not be your final model. So this, again, is not always a solution that's going to be the best choice to remove outliers. The third technique is something of a hybrid model between them. It relies on using a clustering algorithm so that you'll group all of the data into clusters. And basically, so you're going to find and measure the distance between the various points and the various clusters. And then clusters that have very few observations then are deemed to be outliers. So this is kind of equivalent to having a range of these values are unacceptable, but it's also equivalent to rejecting observations that do not fit the model. Since you've created different groups and you say these people didn't fit within any of those groups, so I'm going to discard them. So it's sort of a hybrid between acceptable values and a predefined model. In any case, all three of these you need to approach detection and removal of outliers with caution. You need to be certain that's what you want to do before you make that choice. So one last time again, we're going to go into KNIME and in the node repository, I'm going to use the outlier removal tool. And I'm just going to drag this up and I'm going to connect it to my data file. And I have several different methods. I can do this with box plot, but the mean and standard deviation is one when I use this tool, it's what I use. And I'm going to say anything more than 3 standard deviations from the mean are how I'm going to decide to reject something. And I'm going to say I'm going to use the total number of gifts as the measure of grouping. And when I execute this, I've got 7,500 records that have been deemed outliers based on total number of gifts and total given. And the second output are the 42,000 that have been kept. And this is what's going to allow me, again, theoretically, if you wanted to move forward. That's a lot of removal. To get rid of 7,500 rows out of a total of 50,000, that's darn near 15% of your data. So maybe I got too aggressive, and maybe I want to start saying maybe you got to be at least 4 factors off the standard deviation. And I might look at it now and say, now how am I doing? Well, 7,800 really didn't help. Means those people that are out there are out there. But again, my job now as a data scientist, I'm going to research this and make some decisions about, is this bad data, bad collection data, bad edited data, or is this somehow potentially real? Because I need to know this information. That completes this chapter of the class. Feel free to move on to the next chapter.